Our speaker today is Hua Wang from Georgia Southern University, and he will be speaking on graph invariants and extremal trees. Thank you, Hua.
Thank you for the introduction, and I appreciate the opportunity to speak here. So I will be introducing this concept of graph invariants, which is very often called topological indices and other names in other literature. But I'm mostly interested in the extremal structures that maximize or minimize certain things. So a lot of this work sounds like extremal graph theory, but it also involves, I think it's more like just basic combinatorics, I guess. And this contains joint work with many collaborators, though I didn't list their names here. Let's see. So there are many graph invariants, and you will see, but I will start with one that I first heard of when I was in grad school, and it is called the Wiener index. It has more than 10 names probably, and the definition is very simple. If you take a graph and you take the distance between a pair of vertices, that's what this notation is for, and you take the sum of all these distances over all pairs of vertices. So basically, and that gives you the so-called Wiener index. This was not first called the Wiener index. It was called the total distance, sum of distance transmission, and it has applications in many real-life optimization problems. And we knew it as Wiener index behind a story of a chemist named Harry Wiener, who basically at some point discovered that if you take the structure of a chemical compound, making each atom a vertex and each bond an edge, and then this total distance between the vertices, which essentially corresponds to how close the atoms are inside a chemical compound, corresponds to things like boiling point, surface pressure, so on and so forth. And so he chose to use W to denote it, and later on it became the Wiener index after his last name. And this was well known in chemical graph theory, as opposed to in IT or traditional graph theory where people have many other different names for it. So that's where it was from. And like I said earlier, that we are most interested in what structures maximize or minimize certain concepts. So if you look at all the tree structures, so of the same number of vertices, then which one maximize the Wiener index, which one minimize the Wiener index, basically corresponds to, say, creating a efficient network using the minimum so that everything is as close to each other as possible, these sort of questions. And it turns out that the answer is very easy, that it is minimized by the star and maximized by the pass. So even if you didn't know these definitions before, it's pretty straightforward what they are. And this is quite easy to prove, as a pass is intuitively as far apart as you can pull the vertices from each other. And the star is as compact as possible to make this whole structure. So this is the starting point of this talk. And then it turns out that there are other graph invariants that are also maximized by the star. Well, they also share the star and the pass as the extremal structure. One of them is the so-called number of subtrees, and well, whoops, how do I go back? And it turns out they are maximized by the star and minimized by the pass. So starting from here, you can start observing this interesting observation, I guess, that the winner index and the number of subtrees are very often opposite to each other. So the more compact the graph is, the shorter the total distance is, but the more number of subtrees there are. And the more stretched out the graph is, the larger the total distance is, and the fewer subtrees there are. This correlation will be discussed more a little bit later, but that's why we introduced number of subtrees here. And back then, when I was in grad school, one of the questions was, well, so we know that the question is easy to prove for star and path among general trees. What if it's for binary trees? And this comes from some applications that has binary structures. So I'll skip those. But I want to mention that the binary tree here, they are not rooted. So every vertex has degree exactly 1. Well, has I want to say every vertex has degree exactly 1 or 3, but this would be a contradiction. But the main point is that there is no root, which has degree 2 normally in computer science. And it turns out that under this constraint, we don't have path or star anymore. So instead of a path, you have this so-called binary caterpillar. Essentially, you have a path, and then you have one and exactly one pendant edge at each internal vertex. And you have this so-called good binary tree, which I skipped the formal definition, but essentially you just start from one vertex and then basically keep adding these cherries to it until you run the vertices. This way, it's basically trying to push the vertices as close as possible to this one on top, kind of like in the case of a star, except that you are not allowed to have a star because every vertex has degree at most 3. So this is the best you can do. The proof is a little bit more technical than just this, but intuitively, it's very easy to understand and believe these observations. And one of the main motivation for this was this so-called number of parsimony alignment in the study of phylogeny. Basically, the number of, I don't claim to really know what this is, but translating to graph theory, it is the number of subtrees containing some leaf in binary tree structures. And this number will give the bound, the maximum number, will give the bound to the time complexity of some algorithms that people are interested in. So, and it won't be too hard to believe that instead of looking at number of subtrees, if you look at number of subtrees containing some leaf, it's exactly the same structure that maximize that number. So that's what this was about. And then following this structure, people are also interested in how to count this exact maximum number. Like I said, the maximum number was supposed to be bounding the time complexity. So in order to count the number of subtrees in such structures, you have to figure out a formal way of partitioning n so that you can say, well, when n is this large, you have this many vertices on what layer, that sort of things. And this is the formal definition, which I have to be honest, after all these years, I barely remember the details. But it was based on that so-called good binary tree that is supposed to be the binary version of the star in our case. And this partitioning was actually generalized to a formal sequence of numbers, the details of which I am not able to explain. But so that was a connection between the winner index, or in another, sometimes we call it a representative of the distance-based graph invariant to the number of subtrees, which is a representative of the counting-based graph invariant. And now if you go back to the winner index itself, the original application was on chemical compounds, in which case the degree of the vertices is also very often restricted, in which case, if you have a carbon, you cannot have degree more than 4, something like that. So it was interesting to, excuse me, it was interesting to consider these extremal questions for graphs or in particular trees, in this case, under degree restrictions. So the first such result was among trees with a given maximum degree. And then because of the fact that each corresponds to a specific degree, so it was pointed out that, well, it might be more interesting to look at graphs with a given degree sequence or trees with a given degree sequence. And it turns out that the winner index is minimized by something that looks like this. Now, once again, you look at the structure, it's really not that hard to believe that this minimizes the total distance, because with a given degree sequence like this, your goal is to push everything towards each other, and you might as well start with something. Think of it as the center of this graph or the center of the star, except that star is not an option here. And then if you want as many vertices to be close to this vertex as possible, you want to give it the largest degree. And then you want as many vertices to be close to the neighbors of it as possible. So you give it the remaining largest degree, in this case, 4, 4, 3, 3. And then you keep going down the degree sequence. And that's why it was named the greedy tree, I guess, because the process of constructing the structure is greedy. It's very intuitive, really. You start with one point and then just keep adding stuff to it in a greedy kind of manner. And it was shown that this does indeed minimize the winner index, so the total distance, and also maximize the number of subtrees. And then there are many graph invariants of the similar nature. So I'm going to just show a couple of them here as an example. One of them is called hyperwinner index, and as you can imagine from the name, that it was introduced about the same time along with the winner index. The definition looks a little strange, but it has a simpler explanation, which is really just the what is it? Which is just sum product of the number of vertices on both sides of an edge over all edges. No, that was the winner index. And in this case, it is over all paths. That's what it is. But that's not important. The important thing is that the hyperwinner index is a sum over all pair of vertices and of some formula of those distances. And then there's this Harry index, also originated from chemical graph theory, where you take the sum over all pairs of vertices, but you take the reciprocal of the distance. And the main interesting thing about this is that this is an increasing function, and this is a decreasing function of the distance. And then there's this other concept called the terminal winner index, where you take the sum of all distances, but not over all pairs of vertices anymore, but over all pairs of leaves. So this was named as terminal winner index for its application in chemical graph theory, but also at the same time proposed to be the gamma index in the study of phylogeny. In a collaborator of mine's PhD thesis, actually. And yeah. And the reason that I pointed this three out is because these are all maximized or minimized by the greedy tree as well. I think that's how greedy tree, this concept gained its somewhat popularity, because it maximizes and minimizes so many different things. In particular, the terminal winner index is minimized by the greedy tree, just as the winner index. The header index is maximized by the greedy tree. So remember that the header index was defined to be the sum of the reciprocal of all those distances. So it's not hard to believe that whatever that was minimizing the distances actually maximizes the reciprocal of it. And this led to a general theorem, which is way more interesting than all the individual extreme results, in my opinion. That says if you take the distance between two vertices and plug it into a function, some function f, and then you take the sum of this value of that function over all pairs of vertices, and this value is always minimized or maximized by the greedy tree, depending on whether this function is increasing or decreasing. And that's not the end of it, because as you notice that greedy tree was only the counterpart of the star in our study among trees with a given degree sequence, right? But at the beginning, we started with the star and the pass. Now that you have greedy tree, what about the counterpart of the pass? In binary trees, it was a binary caterpillar, which trees with a given degree sequence. At some point, I conjecture that actually I even came up with that a greedy caterpillar exists to be the counterpart of the greedy tree, to be the opposite of greedy tree, and I was wrong. So what is that extremal structure then? And it turned out to be a very difficult question. An older result shows that such a graph, in this particular case, the tree with a given degree sequence that maximizes the winner index has to be a caterpillar. And the proof is quite easy to explain without going into details, is that if you assume that it's not a caterpillar, which means you start with a pass and then not everything is a pendant edge here. That means there is something like this. So that's the opposite of caterpillar. Something is not the leg of the caterpillar. And then you look at this bubble, everything in this bubble, and we say that you can move it either to this side or to that side. And by moving it, we mean we break all these edges from Y to whatever its neighbors are, except for this, and then attach them here. And as you can see, this simple operation does not change the degree sequence. So basically, whatever the degree of Y is became the new degree of XL. And XL was a leaf, now Y is a leaf. So the degree sequence doesn't change. And whatever we do here is moving a bunch of stuff to either this end or that end. Now, one of these end is further away from more vertices. So, and we just pick that one. Basically, one end will get the winner index smaller, the other one will be bigger. So, so that I always thought that that argument was very nice because it's intuitively so easy to believe. And what this shows by contradiction is that T, the extremal tree that maximizes the winner index, has to be a caterpillar. And like I said before, that the naive thought that a greedy caterpillar exists is wrong. So the real question is, what caterpillar maximize the winner index or maximize the total distance? And this turned out to be extremely hard. Now, the thing is that once you know that the extremal tree is a caterpillar, all that matters is that how do you arrange the degrees of these vertices along this backbone of it. And if you want to put the vertices as far apart from each other, then intuitively you want to put the larger degrees on the two ends and the smaller degrees in the middle. And the naive greedy algorithm for doing that turned out to be wrong. The simple story is basically that the extremal structure will depend on the degree sequence. So, but one can get a formula for it, which is this, where this yi, and yj are just the degrees minus 1 for technical reason. The explanation is again very intuitive. That if you look at every edge and you think about how many times this edge can be used as part of a pass, it's just a number of ways to pick an end vertex here and an end vertex here. In other words, the number of times this, well, the number of vertices here times that because a pass has one and there one here, right? But that means if you look at, let's see, two bubbles here, how many times will the number of vertices here and there serve as the two end vertices of a pass? Well, they will serve as two end vertices of a pass that contains either this edge or that edge or that edge. In other words, it will be used for this many edges there. And this is where the j minus I comes from, and this y times yj comes from the number of vertices here times the number of vertices here. So I did skip some technical details. That's why we also have a constant term there. But this is a basic idea. And what's interesting about this is that this represents the winner index of a caterpillar with a given degree sequence as a quadratic form. And all that matters is the permutation of these degrees. And with this representation, one can easily show that the degrees of the vertices along the backbone of this caterpillar have to satisfy this so-called V property, which says that the degree has to go from large to small and then large again, the V property. And if that's not the case, like here, then same idea as before, you can consider these three bubbles. We switch the middle one, the larger one. If it's bigger than both of them, that's a contradiction of the V property. You can either switch these two or switch that two. One of them will give you a larger winner index. And so that proves that. And after all this, the fact that the formula can be represented as a quadratic formula and the V property, so we saw that, it turns out that there is a fast algorithm to find the extremal tree under this condition. And this was done by a group of people in discrete optimization. So this result was interesting because normally a quadratic assignment problem is it NP hard or NP complete? I don't remember, but so the fact that you can find the fast algorithm, I think it was polynomial time, for the winner index is interesting, and that was considered as a solution to this problem, and was done in a way and by a group of people that are very different from the original ones starting it. So that was interesting. Still about extremal structures, dealing with things related to winner index and so on and so forth. I just want to mention that I mentioned earlier the terminal winner index. It turns out to be related to the study of tibial neighborhood in phylogeny. It's interesting because it was proposed about the same time in chemists and in phylogenetic study. And then that general result about a function of the distances and taking the sum always maximized and minimized by the greedy tree. It was applied to many so-called chemical indices for their application in chemical graph theory, such as winner index, Harry index, and so forth. And also more on the pure mathematics point of view, it was further shown that the greedy tree not just maximizes the total number of subtrees, it actually maximizes the number of subtrees containing the root, And the proof is also much harder. But I just want to mention here. And at the beginning, also I think in my abstract, I mentioned correlation. So I said that winner index and the number of subtrees are good examples of two graph invariants that are negatively correlated to each other. And this was sort of justified in this paper, where a bunch of graph invariants were studied, and it seems like most of the time, the larger the winner index is, the smaller the number of subtrees are, and vice versa. Now we say most of the time because it's definitely not true without most of the time. There are counterexamples one can easily find, but in terms of extremal structures, for a long time, all the extremal structures that people know of, this negative correlation existed. So, and along that line, we were interested in looking at this a little more. And this involves looking at extremal structures that not just maximize a single function of something, I guess. Instead of just maximize or minimize the global function of the graph, we want to involve some local version of the graph invariant. That was the content of these two papers, which I will try to at least show some idea of. For that purpose, we define this local version of the graph invariant, which turned out to be a general, which later on turned out to be generalizable, I guess, to many other concepts. Where instead of looking at the sum over all pairs of these distances, we look at the sum of all the distances from a single vertex. And once again, this was not first studied based on chemical indices or chemical graph theory, but it's related to the winner index in this way. And also, instead of looking at all the subtrees, we look at only the number of subtrees, that contain a particular vertex V. So we tend to call this the local version of those two graph invariants. And when you have the local version of something like this, you can define the middle part of a structure. There were a series of studies of middle parts of graphs and trees in particular based on graph invariants, which we won't mention here. But for these two particular invariants, the middle part of the graph usually maximize the number of subtrees and minimize the total distance from it, which is kind of intuitively clear, because if you think of a star, the middle part is obviously the center of the star that's contained in most number of subtrees. And also the distance from the center to everything else is minimized. Well, so it's a center. And on the other hand, the minimum number of local subtree number and the maximal local distance is at leaf. So based on this, people were interested in these ratios. And what we have here is the quotient of the local graph invariant at either two leaves or one leaf, one in the center, or the global value over the local version in the center, or the global value over the local version in the leaf. And the extremal problems was studied for all of this, and for both the winner index and the number of subtrees. So on the application side, this mainly further studies how these two concepts are related to each other. On the pure math side, this was just much more difficult than the regular extremal problems. So one example, one simple case of this study is, let's say if you want to maximize this ratio and minimize that ratio. So that is to say that we want this pair of vertices and we want the ones containing V to be much larger than U or vice versa. Depends on whether you are looking at the number of subtrees or the distance. And in terms of number of subtrees, you want to make this one containing as many subtrees as possible, and that one as few as possible. In terms of the winner index, you want to make this one close to as many vertices as possible, and that one as far away from most vertices. And then the proof is simply to take all these hanging branches, put them over there, right? And then through some calculation, you can show that, well, when this is a hanging star, then this comet or room, as people call it in graph theory, um, achieves maximum value for something like that and minimum value for something like this. Um, so I gave some examples of other distance-based graph invariants earlier through the variations of winner index. But as far as for counting-based graph invariants, it's not just number of subtrees, only that it's the concept that I'm most familiar with. There are many areas actually, including the number of independent sets, the number of matchings, and the number of dominating sets, walks, anti-chains, so on and so forth. And these first two were maybe better known or more studied than the others, still because of their application in technical graph theory, and there go with some special names as well. But what was interesting is, unlike in the case of winner index and the number of subtrees, where the extremal structure was so intuitively natural to see, the star, the path, the greedy tree, so on and so forth, the caterpillar. In this case, the structure is not natural at all, the extremal structure. And what happened here is that you had the largest degree here, attach the smallest degree, and then attach the largest degree and the smallest degree again, again, again. That's how, to me, that's how this structure is formed. Simply put, the technical definition is much more complicated. But it turns out that this maximize or minimize this number of independent sets or matchings, which makes sense if you think about what they require, right? Because the independent sets and the matchings both require the items counted to be disjoint. And this alternating max min degree achieves that in some sense. So that's my attempt at explaining the structure intuitively. And that was what this theorem was about. And what's more interesting is that this number of independent sets and number of matchings turned out to be another pair of highly negatively correlated graph invariants. So this negative correlation was later on verified for a bunch of other extremal structures as well. Another graph invariant that's also maximized or minimized by a similar structure where you have to alternate the large degree and minimum degree is so-called Randish index. And the name once again comes from chemical graph theory from the applications. But the definition is very simple, where you take the product of the degrees of adjacent vertices, and then you take a power of it, and you take the sum of that. And And it turned out that this is either maximized or minimized by a structure similar to what we just seen, depending on whether this power is positive or negative, as you can imagine. And this also introduces a new category of graph invariants, commonly called degree-based indices, as opposed to distance-based or counting-based. And there are many, many variations of it, so I will list all of them, but here is just an example to show you how complicated they can get from real-life applications. I've never studied this, but as you can see, it's still the product of degrees over all vertices on a certain path, probably over all paths of a certain length. But I imagine that it's extremely difficult to study extremal problems for these sort of things. But I do want to show a general result, just like what we did for the distance-based indices here for the degree-based invariants. What we do is we take the degree of two adjacent vertices, we plug them into a function, and we take the sum of this over all adjacent vertices. And depending on whether the function is that or not, or the opposite. So, and this is just a fancy way of saying that the second derivative is non-negative. And of course, here the function is discrete, so we don't really get to use that here, but that's what this condition means. So if our function f satisfies that, then it is always maximized or minimized, depending on whether it satisfies that or the opposite of that, by the greedy tree. Which was interesting in a way because greedy tree was already known as minimizing and maximizing so many different things. And also it's natural that if you're dealing with degrees, putting all the large degrees together, like in the greedy construction of greedy trees, is the way to go. And this applies to things like this. For example, if you take the power of the product of adjacent degrees and take the sum, or a power of the sum of adjacent degrees, or something slightly different, or even this. You can show that these functions, like square root of x plus y minus 2 over xy, does satisfy our condition, and there go the general theorem applies to them. So, and so I'm taking this opportunity to introduce to you a bunch of variations of degree-based graph invariants as well. Another type of study in the work of graph invariants and extremal graphs is to not just finding the extremal graph, which we have seen many cases of greedy trees in this talk, but also to compare extremal graphs with different degree sequences. So what that means is, let's say you have two degree sequences here, and we say that one majorizes the other if, well, first of all, you can compare them if they correspond to the same number of vertices. Ergo, the second condition must hold, the sum must be the same. And second of all, if this one has a larger degree than this one, when they first differ. Yeah, that's the word I'm looking for. And in this case, we say that this degree sequence majorizes the other one. Okay. And the interesting result on this is that once you establish this majorization between degree sequences, you can actually compare the extremal graph with each degree sequence, according to whether one degree sequence majorizes the other or not. And so here is the result in the form of this generalized degree-based environments. But the majorization of greedy trees in terms of the degree sequences was actually studied way before this. But here basically it says that if one, where is it? If one degree sequence majorizes the other, then the corresponding greedy tree for that degree sequence is better than the other greedy tree corresponding to the other degree sequence. Better in the sense that it's either bigger for something that they maximize or smaller for something that they minimize. And this once again was interesting because it has applications. When you compare all trees with all general trees, then the 1 degree sequence that says, I don't know, n minus 1, 1, 1, 1, 1, 1, 1, so on and so forth, obviously majorizes all other degree sequences. And therefore it shows that star is the extremal tree. Or if you look at extremal trees with a given maximum degree, then because, if you want your degree sequence to be strong, to dominate all other degree sequences, you want the bigger degrees to be in the front. But with a given maximum degree, you can only put, as big a degree as possible to the front like this. And this generalizes to something called complete delta trees, which I did not introduce in this talk. Similarly, for graphs with given number of leaves, so if you have fixed number of leaves, what tree maximizes or minimizes certain things? Well, with this result, one can see that the dominating degree sequence have the largest degree and then a bunch of twos and a bunch of ones. That results in a tree that looks like this. Basically, it's a star that is subdivided. Each edge of the star is subdivided into a path. And it also applies to graphs with a given number of, with a given independence number or matching number. And the proofs of this two relies on the fact that once the independence number is fixed, there are only so many ways to manipulate the degree sequence to make it dominating. And they all end up with as big as possible a number of leaves. So, and the study of graph invariants and extremal trees also left many difficult questions, really. In my own work, I try to find what I can do, but in general, for trees, it's most of the time easier than for general graphs. And one would think that for cyclic graphs, that means a graph with one and only one cycle in it, it might be easy to do. But it turns out that even for cyclic graphs with a given degree sequence, some questions turned out to be much more difficult and still open to this day. And then the extremal problems dealing with local versions of graph invariants, like I introduced earlier, are much more difficult as well. And also, it's always useful to find uniform proof or statement for extremal results. And for general graphs, there are quite some work done actually, but none as specific as in trees, again, because of how difficult they are. Well, I shouldn't put it that way because complete graphs and paths are obviously extremal in many cases among general graphs, but when you put other restrictions on it, it became much more difficult. And then when you restrict graph parameters like fixed height or diameter or fixed maximum degree, the question usually gets much more difficult. One example of such problem is the following, that that one would never expect to be so difficult, I guess, where we wanted to minimize the number of subtrees in a rooted tree that contains a root. So, so if you look at this, first of all, it's on trees, right? Many people think that everything in trees should be easy, at least not too hard. So it's in a rooted tree, and we're only interested in the number of subtrees containing the root. Imagine that you can count this, right? You can count the number of subtrees containing the root as in the number of subtrees containing the root in here times that times that, and we want to minimize it. Um, the only extra parameter, the only extra constraint we added is that it has fixed height. And without fixed height, obviously, we're just gonna extend this infinitely long as possible. Then there are as few subtrees possible. But with fixed height, you cannot extend this infinitely long. And we simply cannot solve the problem. And this was after a tremendous amount of effort, where we end up with the statement that the extremal structure that does this must be of this shape, where we call each of these a split. So that means every leaf must be of the maximum height, right? So they're all here. And then every branch here can only have one split. You cannot have more than one thing coming out of it. And then there's one big split, and others are a smaller split, but have to be evenly distributed. So this is the best we can do. And you have formulas restricting how big this can be, so on and so forth. But up to this date, we still cannot figure out what actually minimize it. So if you, yeah. But anyway, this is just an example of some questions where it seems to be so simple, but it's just very difficult to prove. And I think this is, I'm sorry, that was my alarm clock, but it seems like I'm right on time. So thank you for your attention.
Thank you, Hua. That was very nice. Are there any questions? So I had a quick question. What does it mean for an invariant to be increasing or decreasing or something? I think at one point we had talked about a result that applied for an increasing or decreasing invariant.
Yeah. So the invariant is this, and this is defined as the sum of a bunch of values when a function was applied to that distance. And when I said increase, I probably said the wrong thing. I do that all the time. But what I meant is when this function is increasing or decreasing. So if you think of the winner index, which is basically the identity function, which is obviously increasing. When you think of the Harry index, which is a reciprocal, basically it's 1 over x, and which is obviously decreasing. And by increasing, decreasing, I meant this function. And then when I take the sum of it, you get this particular graph invariant, which can be applied to many specific topological indices.
Thank you.
Mm-hmm.
And I will stop the recording.